All right, so we're now almost at the end of the course. We're now gonna reap the rewards of everything that we've done and use it to study what's called the ideal class group in chapter 4, and then the next chapter, chapter 5, we'll use it to solve some Diophantine equations. So this is the class group is somehow what we've been working up towards this whole time. We're going to pretty much use a lot of the theory that we've developed, like computing discriminants, computing rings of integers, factoring ideals, factoring ideals into prime ideals. All of this is going to play a role. But I need to somehow tell you what the what this thing is. So we talked a lot about how ideals look like in Dedekind domains, and one of the things that we saw was that a Dedekind domain is a principal ideal domain if and only if it's a unique factorization domain. And somehow we've seen examples where our Dedekind domain isn't a unique factorization domain. Or at least I think we've seen examples. But it turns out that for our rings of integers, there's lots of times you might not have a unique factorization domain, which means that your ideals, by this equivalence, this means that the ideals won't be principal. And so somehow we want to be able to deal with this, the fact that our ideals aren't principal. And we want to measure how far our ring of integers is from being a principal ideal domain. So we somehow want to see, we know already that for every ideal can be generated by 2 elements, but somehow we want to see how many ideals aren't principal in our ring. I'll make this precise, and this is what the class group is going to do. So, let me just start with some reminders. Recall that we defined fractional ideals. And we said a fractional ideal is principal if it's of the form someone you'd expect. It just looks like something that's integrated by x, which is just like all the multiples of x times y with y in OK. The only difference is that here, for x, here x is allowed to be some element of your field, doesn't have to be an algebraic integer. So you take some element in your field and then you just consider all multiples of this thing. If you think about it, this wouldn't generally be an ideal in the normal sense, because for ideals, we're only talking about ideals usually inside of this ring, but x isn't an element of this ring. So this doesn't quite make sense as an ideal, but it makes sense of what we call a fractional ideal. Essentially, it's basically an ideal up to some fixed denominators that have showed up. And the thing to note is that if you have 2 fractional ideals, you can multiply them together and you get another fractional ideal. So note that if x and y are fractional ideals, let's just say principal fractional ideal. And so is their product xy, which is just going to be the ideal generated by x and y. The same sort of thing happens that we saw this for ideals before, and the same thing works for fractional ideals. And moreover, in this case, we actually, because we're working with fractional ideals, we actually have like an inverse. If you do this times this ideal, then you get ideal generated by 1, which is just all of OK. So this means that the set of fractional ideals forms principal fractional ideals forms a subgroup. So this means the set of principal fractional ideals is in fact a group. Well, is in fact a subgroup of the. We talked about fractional ideals forming a group, so it's a subgroup of the group of fractional ideals. And essentially, because we want to measure how far our ring is from being a PID, we want to measure how far our ideals all from all being principal. So somehow we're going to look at the group that you get by taking all ideals and quotienting out by these principal fractional ideals, and that's what we're going to call the class group. So I'm going to let so for K a number field, we let PK denote the the group of fractional ideals, the group of principal fractional ideals. That's what P stands for. All right. So here's the big definition. So this is definition 4.0.1. This is the class group. So the class group of K, where K is a number field. Let me just it's tradition that I write this, so I should start. So let K be a number field. The class group of K is defined to be the quotient group. That we get by another CLK, and this is, remember we had this notation, JK over PK. So I'll remind you that JK is the group of all fractional ideals. So we checked before that fractional ideals form the group because I had an inverse, and I just told you that the principal fractional ideals form a subgroup. So I can pick a group and quotient out by a subgroup. This is all abelian, so there's no normal. You don't have to worry about anything normal. It's called the elements of this thing the classes of an ideal. So we call the elements ideal classes. Called ideal classes. And I'm going to just give you some notation. If A is a fractional ideal, I'm going to just put some square brackets around it to denote its class inside of this class group. So this is some ideal, and I just think of the quotient up to principal ideals. We know by square brackets A, it's a class in K. In my class group. And lastly, what we want to study a lot is the size of this class group and what the structure is. But we're going to give it a name, so I'm going to let HK denote the size of CLK, and we call this the class number. Great. So let me just recap. Before, we looked at ideals. We looked at a slight generalization of ideals. We heard these things of fractional ideals. We showed that this thing formed a group, and we called this group JK for K a number field. And what we want to study now is the quotient group that you get by taking this group and quotienting out by all ideals that are principal. So somehow you want to say, let's ignore all the principal ideals. I just care about the ideals that aren't principal, because I want to somehow measure how far my ideals are from principal. So think of it as the bigger this group is, the less of my ideals are principal. So the weirder my group is, the further away it is from being a unique factorization domain, because it'll be a unique factorization domain if and only if it's a PID. So this is the class group. This is this invariant that you want to study of our number field, and its size is somehow important in this its own name, the class number. I'm just going to use HK to denote this. And what we're going to see in a second is that this group is finite. So this number is actually some finite number. It's not infinity. So let me just give you some remarks about this definition. So remark, just so you can get some idea of what this looks like. So note that in the class group, the identity is given by the class of a principal ideal, because it's quotient number of principal ideals. Principal of fractional ideal. Which we denote. I'm just gonna always just denote it with like the class of 1. Also note that. Furthermore, I don't need the dots. If I have A and B fractional ideals, then so remember that this is a group under multiplication of ideals. So when I defined the group of fractional ideals, I defined it as a group as under multiplication. So I'll multiply my ideals together. That's my group structure. I should have said that. It's a group under multiplication. So if I have 2 fractional ideals, then they'll have the same class. What does it mean for them to have the same class? This will be the same thing if there exists some principal ideal or principal fractional ideal. Ideal, say alpha, such that one ideal is the product of alpha times b. So if as ideals they differ by a multiple of a fractional of a principal ideal, then the classes that they're going to do will be the same, because I think of it as I've quotiented out by the principal ideals. So as a set, just make this clear, we have or coset. We have the class of A is just all ideals, from X times A, such that X is similar to K. Great. I should say coset. It's a coset representative. This is what our coset did. All right, so some more remarks. So if our ring actually is a principal ideal domain, so if every ideal is principal, then this JK is exactly this PK. So these two the group and these two groups are the same. So this class group is trivial. So I'm going to note that. Note that if OK is a PID. Well, note that OK is a PID if and only if the class group is trivial. Note that I was talking about OK being a PID. This implies that all fractional ideals also have to be a principal, because fractional ideals up to a multiple just look like a normal ideal. And so we know that. Note that OK being a PID is the same thing as the class group being trivial, i.e. being just element 1. Moreover, what I was saying before, since a Dedekind domain is a PID if and only if it's a UFT, something that we proved before. That's only if it's a unique factorization domain. This means if you just compose these things together, that OK is a UFD if and only if the class group of K is trivial. So this really is that the class group not being trivial means that you can't be a UFD, which means that your structure is a little bit more complicated. So here's the first theorem. Here's the theorem 4.0.2, which I said what it was above, which is that the class group is finite. So number field, then HK, the class number. So remember, this is the size of the class group, is finite. So to prove this, I need to make use of one special result. And this result is the reason for the existence of chapter 6 in the notes, because it needs a whole bunch of machinery just to prove this one theorem. So I'm gonna state it now. We're gonna do the rest of our calculations with class groups and so on, and then the proof will be in chapter 6 if we get to that, or I'll just leave you to read it. So I'm gonna say to prove this, we need the following result. Well, technically, you can prove that this class group is finite without this result, but then it wouldn't allow you to compute any class groups ever. So this is the result that we want, so that we can actually do some computations. 0.03. So the K be a number field. With, as usual, R1 real embeddings and R2 complex conjugate embeddings. I'm going to let the degree of this field be n, and I'm going to take some ideal A and OK, an ideal. Then what's the result? Then there exists some little a in my ideal such that the following holds. This is going to look a very strange result, such that the size of the norm of this element, from K to Q of A, little a, the size of this element is less than or equal than the following weird quantity. This weird quantity is called the Minkowski bound. It's n factorial, n is the degree of my field. It's n factorial over n to the n times 4 over pi. Yes, this is pi as in 3.14 blah blah to the power of R2 times the absolute value of the discriminant of your field to the half. So you take the absolute value and take the square root times the norm of your ideal A, the norm of the ideal that we took. So there exists some A in ideal such that the norm of A is smaller than this quantity. This is the theorem that I'm going to assume. This is the theorem that needs to be proven with the stuff in chapter 6. The fact that this is some pi showing up, this is because you end up having to embed your number field into like a bunch of copies of Rn and then compute the volume of some surface or some object. But I'm going to give this this thing a name. So I'll say proof C chapter 6. But here's something that we're going to give a name to. So definition 4.0.4. Definition not found. The quantity. So this quantity here this, forgetting the norm, so just this bit of the bit that doesn't depend on my ideal. So this depends just on my field. This is another invariant of my field. This is known as the Minkowski bound. And we denote it by mk. So for a number field of degree n, this quantity n factorial over n to the n over 4 pi to the number of real or complex conjugate embeddings and the square root of the discriminant, this is called the Minkowski bound. Okay, so this is the theorem that we're going to prove now, but I'm going to start moving towards proving this theorem here, but we still need some some of the results. So here's a small proposition. So that we need beforehand. So proposition 4.0.5. Let K be a number field. And I'm not sure I've changed my notation. I'm going to let C be an ideal class in the class group. Then C contains an ideal little a. So an ideal frac A and OK. So this is the class. Remember, this is a class in the class group. So this is a bunch of a class of fractional ideals. So it's like take a fractional ideal and take all multiples by a principal fractional ideal. But whatever all of these, this coset that I defined up here, the coset it has one of the elements inside of it is a standard ideal in OK, which has a special property. So it contains an ideal A in OK such that the norm of this ideal is less than the Minkowski bound. So the Minkowski bound tells me, if I look at the class group and I look at the representatives for the elements in my class group, then I can always take a representative given by an ideal with norm which is smaller than my Minkowski bound. So if the norm of the Minkowski bound is very small, then the norm of every ideal can be represented by an ideal of very small class, very small norm. Okay, so this I will prove now. So prove, consider the class C inverse. This has a representative which is an ideal, which you can take to be an ideal, say B of OK, by this theorem that I haven't proved, this theorem 4.03, by theorem 4.0.3, there exists some x in this ideal such that the norm of this element x, the absolute value of the norm of this element x, is less than the Minkowski bound times the norm of B. This is what this was telling me. The norm of, I had an element, and then I said that the norm of the element was the Minkowski bound times the norm of, was less than the Minkowski bound times the norm of the ideal. So I have to confine some element in my ideal here such that its norm is less than the Minkowski bound times the norm of B. So if I set A to be B inverse times the ideal generated by the fractional ideal that X generates, then if you think about this, this is in the same class of C. This is, I'd say, in the class of C, or in C, which is it's a class. So this is, it's going to be an element of this C. Why? Because, well, B was an element of C inverse, so B inverse is an element of C, and B times the fractional ideal doesn't change what class it's in, so it's still the same sort of thing. So I'm going to set this A to be this thing. So this is some class. This is in my class C, since it's a multiple of B times 1 by a principal ideal. So fractional ideal. No, it just doesn't have to be fractional. In this case, the theorem tells me that X is an OK principal ideal. Moreover, since the X that I took was an element of B, it follows that B inverse times X is actually in OK. So recall what the inverse means. The B inverse is a set of Y and K such that y times b is an element of OK. This is what the inverse of an ideal, of a fractional ideal was. So if you think about what this, we all the elements like this are like this, and then are of this form. They're all y such that y times b is an OK. So if you take one of these elements and multiply it by x, and this still stays inside of OK. So this ideal that I just defined is a proper ideal. Well, I'm guessing it's an ideal in OK. So A is that. So okay, it doesn't have to be proper. I guess it could be the whole thing for all we know. So now by construction, of this ideal that I've defined, we have that its norm, the norm of this ideal A, is the norm of the element of x. This result about the norm of the fraction. You can define fraction. Well, x is okay. Yeah, x is in OK. So this is the norm of this ideal. This little bit of the ideal is the same thing as the absolute value of the norm of the element, and the norm of B inverse. This is an actual ideal, you can convince yourself that this somehow extends to fractional ideals. We have this equality, which by construction is less than mk, right? Because I had this equality, so I know that this ideal divided by the norm. Sorry, this norm divided by the norm of B is less than mk, and this is the ideal A. So this gives a result. So that's the first thing. So I said that every class in my ideal class contains an ideal of small norm, or of norm less than mk. And now the proof of this theorem, the proof that the class number is finite, is really easy, because we know that every class contains an ideal of some norm less than some fixed bound, and there are only many ideals of any given norm. So we're done. So I'll do proof of theorem 4.0.2. Here's the proof by proposition, the previous proposition. Each ideal class C in the class group must contain an ideal contain an ideal of norm at most my Minkowski bound. Now, just finished by this corollary that we talked about before, that there's only many ideals of any given norm. So now by corollary, what is it, 3.4.10, this means there are only finitely many such classes, such ideals. Ideals, thus only finitely many such classes. Thus only finitely many ideal classes. Great. So let me just recap. So maybe this notion of ideal class. Remember, the class of an ideal is just as a set. It just looks like all multiples by this. What I'm saying is that if you look through all this, for any class in the ideal class, if you look through this set, this coset, then you can always find one ideal like this, which has a norm less than the Minkowski bound. And so there's only ever finitely many ideals of any given norm. We proved that before. So if the norm is like 10, this means that every class has to contain an ideal of norm less than 10. So say there's only 3 ideals of norm less than 10. So you can't have distinct classes, or if 2 classes contain the same element, then they have to be the same class. This is what happens in cosets. This immediately bounds how many different classes we can have. Okay, great. So I've told you that the idea of class group exists and that it's finite. Next time what I'm going to do is do a bunch of computations. So I'm going to compute a bunch of class groups for you to see how this is done. And you'll get plenty of experience about doing this in the problem sheets.